Hello and welcome to Chapter 5. Now we finally got through all those data analysis of showing how statistics and definitions to get really more into different versions of statistics. And the first one that we're going to hit on is probability. And I assume that some of y'all have already heard about probability. We hear it all the time when it comes to stats. And for one thing, we can say this: the more that you go through the class, the probability of you passing becomes greater and greater. Yeah. I'm sure everybody's going to pass this course because y'all guys are all awesome. And again, if you have any questions, what's the first thing you do? You send me an email. Alright. So, we know the drill. Let's go ahead and get into our learning objectives for this chapter in PowerPoint. First off, we're going to define the terms of probability, experiment, and event, and outcome. Kind of like a nice little science fair thing. Learning objective 2, we're going to assign probabilities using a classical, empirical, there's the empirical role again, or subjective approach. Learning objective 3, we're going to calculate probabilities, use the rule of addition. And learning objective 4 is going to calculate probabilities using the rules of multiplication. Then we're going to compute probabilities using a contingency table. It's back. Yay! And learning objective number 6. Determine the number of outcomes using principles of counting. I know everybody's like going, yes, I've been waiting for probability. Probability of that is probably zip. But if it is, yay! Alright, so what is probability in itself? It is a numerical value that basically describes the chance that something will happen. The closer the probability is to 0, the more improbable. The closer the probability is to 1, the more likely it will happen. Again, it's a very inclusive number describing the relative possibility, chance of likelihood of an event will occur. So, they actually show this little graph here, and of course, probability our sun will disappear this year. Very, very 0. So, chances Slowpoke will win the Kentucky Derby. 0.2. So, now that's gambling. They shouldn't have gambling in here, because some people may take those odds. Chances of a head in single toss of a coin. It's usually a 50-50 chance. Chance of an increase in federal taxes. Wow. Yeah. Chance of rain in Florida this year. 1. 100%. Yeah, that's usually always the case. Now, you usually hear these in percentages. That's what basically they are. So, sometimes you gotta enjoy the examples they give. And sometimes you're like, but it works all the same. So, we do have 3 key terms that we use in the study of probability. And these are experiment, which is basically observations of some activity or an act of taking some measurement. Kind of like that tossing of the coin. So, it leads to the occurrence of one and only one of several possible results. Then we have, of course, outcome. Well, outcomes is a particular result of an experiment. This is what we want. This is what we want to see. What's going to happen? So, for example, they do have the roll of a dice, which is the experiment. And we actually have 6 possible outcomes. Since most dice, that regular dice, are 6-sided, we do have 6 outcomes. Now, the last term that we typically use is known as an event. Event is a collection of one or more outcomes of an experiment. Okay, so with this, some possible events that they give as an example with the rolling of dice, we can observe how many times an even number will pop up. Since there is 3 out of 6 are even, there's a 50-50 shot. Could actually be a greater, could be less. Observation of a number greater than 4. The probability is a little bit lower, but during our experiment, it might actually be higher, depending on the dice. And observing of a number 3 or less. So, just matters of how the die will roll. And right now, for some reason, that reminds me of Cuphead. Interesting video game if you ever play it. Anyway, then give another experiment. Count the number of members of the board of directors for Fortune 500 companies who are over 60 years of age. And they give plenty of outcomes depending on how many of these executives, which could be a lot bigger, and some events as well. But basically, these are the 3 terms that we're going to be looking at. We're going to constantly look at. Now, with our probability, the fun part here. So, we have the classical definition. Probability applies when they are equal. They are in equal. They're missing an A. An equal likely outcomes to an experiment. Okay, so there is 3 definitions of probability. Classical approach really does come to probability is often applied to games of chance, like playing cards or rolling dice. It can also be applied to lotteries because the total number of outcomes is known before the experiment. If the set of events is collective exhaustive and mutual exclusive, the sum of the probabilities is 1. So for our formula, the classical probability, we do take the number of favorable outcomes, so the outcomes that we want to see, like if it was even, we want to see at least 3 of them, divided by the total number of possible outcomes. And if we're looking at a 6-sided die, we only have 6 possible outcomes, so it's a 50-50 shot. Basically 50% of that event to occur. Mutual exclusive, these occurrences of one event means that none of the other events can occur at the same time. Again, on roll of a die, you're going to have mutual exclusive events because only one could happen. When we look at a collective exhaustive, at least one of the events must occur when an experiment is conducted. Okay, so again, one of the events in our 6 has to happen, which most likely we will land on an even one eventually. Yay! Okay. Empirical probability is also known as basically relative frequency. And when we look at this, it basically occurs when the number of times an event happens is divided by the number of outcomes. So when we look at these, the probability of event happening is the fraction of times similar events happened in the past. Basically, we do our experiment. We take how many times the event that we would like to happen happens, and divide by the number of observations. This is where the classical approach can falter a little bit, because in our experiment we can show that the number of even numbers, which are supposed to be 50% of the time, actually happen a lot less or a lot more, because more of those events happen during our experiment. The law of large numbers. Over a large number of trials, the empirical probability of an event will approach its true probability. Again, if you keep doing it big time, the more that you have, the more accurate it will seem to be getting, because it will happen more often as we go, or less. So we're going to get its true nature. This is why we do see, for example, with vaccinations and clinical trials, they try to get a larger population, a larger sample size, since it is a sample size, and they look for the probability of concerns, stuff that, adverse reactions. And the larger the population gets, the more accurate those numbers will become. So we could see a high number of adverse reactions in a small sample, very small, but as it grows and grows and grows, we may actually see less of that probability actually happening, and becomes more true to its nature. So, for example, also another example as well, a firm using empirical probability is when life insurance companies use past data to determine the acceptability of an applicant, as well as the premium to be charged. Wow. So, they even give an example of Stephen Curry. If anybody knows who Stephen Curry is, he is a member of the Golden State Warriors at the time of this recording, and made 278 out of 302 free throw attempts during the 2017-2018 NBA season. Based on the empirical approach to the probability, the likelihood of him making the next free throw attempt is 92%. That's where we do get our free throw attempt percentage. They always look at historical. All right. Next probability that we can see, subjectivity. Okay. So, subjectivity concept of probability, the likelihood of a particular event happening that is assigned by an individual based on whatever information is available. Usually when there's little or no data available, it will become subjectivity. It will have a lot more bias to it. And because we don't have enough info, an individual evaluates the available information and then assigns a probability. Examples that they have is estimating the likelihood the New England Patriots will be in the Super Bowl next year. And it seems like it's getting bigger and bigger, even though Tom Brady is no longer there. There you got, at the time of this recording, I always have to do that in case I use these videos for later on. They have Mac Jones, and they made the playoffs. So, who knows? Is the likelihood of them making it still high? Yeah, still high, but it's probably less, a little bit diminishing. If they had Tom Brady, it's usually very high. And they have another estimate, the likelihood of the U.S. budget deficit will be reduced by half in the next 10 years. Good luck. The probability is probably not very good. But again, we can only take by the information that we have. So currently, we can be subjective, like the Houston Texans making the Super Bowl next year. Probability is probably going to be very, very low. But who knows? Sports is one of those crazy things that a lot of people didn't think the Cincinnati Bengals will be in the Super Bowl this year. And Yet, they are. So, you never know with sports. That's why probability is very, very hard there. Unless it's actually stats, like certain things they do. Alright. So here's our summary of probability. Got a nice little graph. Follow the chart. So approaches to probability. We can be objective or subjective. Subjective is only that one based on available information. It's objective. We have the classical approach, and it's based on equality, likely outcomes. And then you got the empirical, which is based on the relative frequencies. Can they be symmetric? Yeah. Will they? Who knows? But we'll find out. We got examples. We got other ways to do it. Let's have some fun. So, rules of addition. And we're moving right through these learning objectives. But the rules of addition in itself refer to the probability that any two or more events can occur. The special rule of addition is used when events are mutually exclusive. Remember, mutually exclusive, one of the events can occur. So, special rule of addition, the probability of A or B equals probability of A plus probability of B. That's what the big P is here, probability. So, if the events of A and B are mutually exclusive, the probability of one or the other event occurring is the sum of their probabilities. This can be extended for more than two events. Here in our Venn diagram, that we have event A, B, and C, do not overlap and therefore mutually exclusive. Again, if you've taken an English class, you've kind of seen Venn diagrams. Here is a mutually exclusive one. So again, we can tell that nothing overlaps. It's a good addition. Probability of A or B equals the two of those. So if C could happen, it's not going to be part of ours. So let's bring in an example. Of course, we're going to have practice problems. But again, I see those firsthand right here. So, a machine fills plastic bags with a mixture of beans, broccoli, and other vegetables. Most of the bags contain the correct rate. Okay? But because of the variation in the size of the beans and other vegetables, a package might be underweight or overweight. Which, we like more overweight ones if we're consumers, get more bang for our buck. Anyway, a check of 4,000 packages filled in the past month revealed the following. We have the event A is where it's underweight. Number of packages happen to be 100. So, the probability of that actually occurring is about 2.5%. Basically taking the number of packages that did become underweight and divide by the total. This is where we get in those probabilities of occurrence. Satisfactory, B, was 3,600. Wow, that machine was cranking pretty good, which ended up being about 90%. And overweight, C, was only 300, which came out to 7.5% out of the number of packages. Again, add them all up. Make sure it equals to 1. Always do that. It's good double check to make sure you got all your percentages. So what is the probability that the particular packages will be either underweight or overweight? Well, it's either going to be A or C. So we're going to add A and C together, the probabilities. So 0.025 plus 0.075 equals to 0.1, or basically 10%. which is a low probability on our scale. Again, closer to 0. So, with this, we got a little easy one, right? As long as they're mutually exclusive, addition works. Yay! So let's try to bump it up a little bit. Not a lot, a little bit. Complement rule. Okay? Complement rule is used to determine the probability of an event happening by subtracting the probability of an event not happening. So basically, it's doing the same thing as addition, but doing subtraction instead. So this rule is useful because sometimes it is easier to calculate the probability of an event happening by determining the probability of it not happening and subtracting the result from 1. But they need to be mutually exclusive and exhaustive. Okay? So, here we're using the same example, except this time to find the probability of A or C, we want equal to the probability of basically the complementary of B equal to 1 minus probability of B. So this will equal 1 minus 0.90 or 90%, which will lead to the 0.10, 10%. When it's 3 and you just need to search for the 2, this works. It works for all others. May have to do addition, then minus from 1. Is that probability? Yes. Can it happen? Yes. Is it going to happen in this course? Yes. You're like, how many times are you going to say yes? Well, why not we just go ahead and do it? So, general rule of addition. So, sometimes we're not going to have it always mutual exclusive. So, when the events are not mutually exclusive, and there's a chance for the same thing to happen at the same time. To find the probability of A or B, we would add probability A plus probability B minus probability of A and B occurring at the same time. So it's a joint probability which measures the likelihood of 2 or more events will happen concurrently. So we have hearts, kings. It looks like we're doing some cards here. But probability of us actually drawing a king or drawing a heart, but we do have king of hearts. So we could actually draw both of these in one event. So this looks like more of your typical Venn diagram. If you worked in English when you compare and contrast. Here's where we put everything that's the same, that's in both circles. So, how do we do this? Well, let's give you an example. Because why not? Alright, so going to Florida. Yay, Florida! Woo! We took a sample of 200 tourists in Florida. Shows that 120 went to Disney. Not that neat, but Disney. And 100 actually went to Busch Gardens, which is surprising that they didn't do Universal. Harry Potter, come on. And 60 visit both. I'll tell you this, I was one of the lucky ones. I got to visit both in my freshman year during band. Yes, that was fun. I'll tell you horror stories of Disney later on. if you ever email me and want to know. So, probability of going to Disney exclusively was 120 divided by 200, which is about 60%, 0.6. Probability of a tourist just going to Busch Gardens was 100 divided by 200, which was about 50%. And the probability of a tourist going to both in our sample was 60 over 200, so about 30%. Alright. Now, notice on this, we have sample of 200 tourists in Florida show 120 plus 100, that's 220, and 60 visit both. I have questions about this sample size. Alright, so it looks like somehow their example kind of got off here. I don't even know how they did. Alright, so we're just going to roll with their example here. Because I'm going, well, so it shows that 120 went to Disney, 100 went, yeah, it's because they have some that are the same. That's what's going on. That's how it goes. See, this is where the sample size kind of, you can't total it all up to 100 because you do have that element of some of them went to both. That's 60. Question is, why doesn't each individual add up? But we're not going to go there. This is just for the results that they have. So, for example, we're going to go with the results that they have. Alright. So, when we want to know if the probability of them either going to Disney or Busch, we would actually add that probability up together. 0.60 plus 0.5 minus 0.3 of them attending both at one trip. So 0.6 plus 0.5, that's 1.1 minus 0.3, drops us down to 0.8, which gives an 80% chance that they're either going to attend Disney or Busch Gardens. So, yay! I have to rethink on that sample size because it seems a little off, but I mean, we have to go with the results that they got because we weren't there to actually do the experiment. The problem is that we're not looking at mutual exclusive ones, so that's why we can't do a total of 100 and add it to it. We have that little overlap, which throws a little fun little jibber jabbers in. Alright. Multiplication now. Somebody's worst fears in math is multiplication. So let's try and do this as best as we can. Okay, you ready? Let's do this. So the rules of multiplication are applied when two or more events occur simultaneously. A special rule of multiplication refers to events that are independent. Basically, the occurrence of one event has no effect on the probability of the occurrence of another event. Most likely, the joint probability is the likelihood that two or more events will happen at the same time. And the AAA example that we got, the events are independent because whether a member made an airline reservation or not has no effect on whether another member made an airline reservation. Unless they use it Yelp or something else. But therefore, the special rules of multiplication can be used. Basically, they're just saying it doesn't matter what you reserve is not going to change another person's mind on their reserve. Completely two independent situations. So when we look at multiplication, probability of A and B occurring will equal to probability A multiplied by probability B. Okay. So a survey of the American Automobile Association, AAA, if you ever want to know what AAA actually stands for, revealed that 60% of its members made airline reservations last year. 2 members are selected at random. What is the probability both made airline reservations last year? So if you take 0.6, then 60% times 0.6, since we're looking at 2 completely independent members, once you multiply them together, most likely for those 2 to make airline reservations is a 0.36% chance, or 36% chance of them making it. Okay? Is the likelihood there? Yes. Is it low? Yes. But there's a higher chance of it happening. It's getting closer to 50%. Okay? So again, if it's independent of each other, no effect, then most likely we can go with the multiplication rule. The general rule, which y'all love, the general rule of multiplication refers to events that are not independent. Okay, so we have the special rule and the general rule, which I would think putting the general rule before the special would actually help, but not my call. That's how they put together the book. So it does refer to when events are not occurred because they are dependent. This is called a conditional probability because its value is conditional on what occurred with the first event. Basically, the probability of B is conditional on the occurrence of the effect of event A. Okay? So, basically we're dealing with dependent variables. So more X and Y. So the crazy twist here is the probability of A and B equals the probability of A times the probability of B over A. Basically, given A. That's what the straight bar is. Not over, sorry. I see it, mine automatically thinks division, but it basically means the probability of B given A. Okay? Yes. Fun symbols. Symbols! Little sweet. Alright. So, how about an example? A golfer has 12 golf shirts in his closet. Suppose 9 of these shirts are white and the others are blue. Okay. He gets dressed in the dark. Why not? So he grabs the shirt and puts it on. He plays golf 2 days in a row and does not return the shirts to the closet. What is the probability both shirts are white? Okay. So, we have the probability of getting a white shirt on the first day is basically 9 over 12. He has 9 white shirts. 12 in the closet. That event is now over. He does the same event, or basically experiment, but he's already removed one shirt. So in order to pull the second white shirt, event A has to be taken place for the 2 consecutive days. So this is where we get 8 shirts now that are left that are white, because the likelihood of him pulling the first white one, divided by 11 total shirts. Because remember, 1 shirt is removed. So in order for that to happen 2 days in a row, consecutive days, we have a likelihood of a 55% chance. Which is pretty high. I mean, almost 50-50 shot right now of having that happen 2 days in a row. So, is it not possible? No, it's possible. We got a good probability chance there. Now, how about contingency tables? Yeah, I remember those. So, again, the contingency table is a cross-tabulation that simultaneously summarizes 2 variables of interest and their relationship. The level of measurement can be nominal. There's our nominal again, a little bit later on. So, again, it's there to classify sample observations according to 2 or more identifiable categories or classes. Again, when we look at nominal, that's just basically names and whatnot, not interval or ratio, just information. So, 150 adults were asked if they were older than 50 years of age and the number of Facebook accounts they used. Okay, the following table summarizes the results. Facebook accounts. We have 0, 1, 2, or more over the years of age. With 0 face accounts, we have over 50, 20 yes, 40 no, total of 60. 1, 40, 30, 70. And 2 or more, we have 10 and 10. So, yes and no. So make it a grand total of 20 that we actually had that had 2 or more. So bringing it up to our total of 150. Okay, that's making our contingency table. Again, we can find our probability by basically taking 60 divided by 150 for our total that have 0. Also the same with 50 years of age divided by basically 20 divided by 150 give us a probability, yes, there's 0 with and over 150. So we may actually see this though as well. This is known as a tree diagram. And this is using a contingency table. So when we use the tree diagram, it is going to be a visual that is helped in organizing and calculating probabilities for problems with several stages. Right here on this slide is the contingency table. This is not the tree diagram. You're about to see that. But each stage of the problem is represented by a branch of the tree. We label the branches with the probabilities. So again, we have movies per month, 0, 1 or 2, 3 to 4, 5, 3, basically 3 through 5, or 6 or more. We got A1, A2, A3, A4. Less than 30 in their age, B1. B2 is 30 to 60, and 60 or older. So we got a lot of information here, and we're going to try and calculate a lot of probability here. So this is basically, looks like a survey conducted by the National Association of Theater Managers. 500 randomly selected adults were asked their age and the number of times they saw a movie in a theater. The survey results are organized in our contingency table by the age and by the number of movies attended per month. So, how does this look like in a tree chart or tree diagram? Boom. This is a tree diagram. Yes, a lot more fun, would you say? So we start off with age. So age gets divided by to 3 outcomes. So most likely to be 30 years older or younger, we have a 20% out of our 500 adults to be that age. 45% could be 30 to 60, and 35% be 60 years or older. Notice again, these are mutually exclusive items because you can only be these ages. They don't overlap. Same thing here, mutually exclusive, because it depends on that age and how much they've seen. Again, so we can go the likelihood of somebody being 30 years old or younger and seeing 1 or 2 movies in a given period will be most likely 45%. Again, the rule of addition. Add the 20 plus the 25. Now, again, this is just the probability of each of these items. Since we only had 100 adults being 30 years old or younger, that's our number here when we can calculate the probability of these. So, and then they have the order of multiplication, so forth. So, I think multiplication actually gives them a little bit more accurate. But they're going to be running right about the same. Fun stuff. Alright. Woo! That looks so complicated, yet it just becomes more of a breakdown. That's all this tree diagram is. It's just a breakdown. So multiplication formula. Different multiplication formula. This is mostly for our tree diagrams. So the multiplication formula states that if there are n ways of doing one thing and m ways of doing another thing, then there are m times n ways of doing both. Like how they do that. This can be extended to more than 2 events. For 3 events, we have m, n, and o. Just random numbers that they get. So the total number of arrangements can be m times n times o. Basically, we're trying to determine the number of outcomes in an experiment. The multiplication formula that is used is to find the total number of arrangements for 2 or more groups. Yes, a lot. A lot of fun. Fun. This is where you can see where they try to announce how many outcomes certain things can get, and it can be in the millions to billions. And then it becomes less able to be calculated. This is a probability. This is a possibility that we have to deal with. But for our examples, we're going to try and keep them simple. Again, this is just a beginning stat course. Plus, it's mostly business. So, when the American Red Cross receives a blood donation, the blood is analyzed and classified by group by an RH factor. There are 4 blood type groups: A, B, AB, and O. The RH factor can be either positive or negative. Okay. How many different blood types are there? Okay, so the possible arrangements that we can have is, since we have 4 blood groups, and only two positive or negative RH factors. We'll end up multiplying the two, and we can have a possibility of 8 outcomes. That's all we're doing here. How many possibility of outcomes could we have? How many outcomes should we have, basically? So 4 for the blood groups times 2 of our other variable, times them together, shows us we can have 8. And it shows you the whole tree diagram right here. Alright, next, we have another formula. Like I tell you, gonna have to write down pretty much all these formulas. They are here to stay. Alright. So, in order to figure this out, is determine basically another counting formula used to determine a total number of outcomes is this permutation. And this is any arrangement of R objects selected from a single group of N possible objects. Yeah. So, our formula is basically N objects for probability of R equals N factoid. Explanation points are usually factoid. Divided by N minus R factoid. It's been a while on that one to say that correctly. But basically, 0 to the factoid, to the exclamation point, basically, is equal to 1. Excel does have a formula that we'll try and look up that will calculate permutations when we actually get into the practice problems or the homework, either one. We'll try and look up the Excel formula for that. So again, there are 3 electronic parts to be assembled, so N equals 3. Because all 3 are to be inserted into the plug-in component, R also equals 3. Okay. So this will equal 3 to the factoid, and basically all that means is basically 3 plus 2 plus 1 plus 0. That's all breakdown. Divide by 3 minus 3, which is factoid. Happens to be 0 factoid, which is 1, so 1. So 3 divided by 1, what? How they get to 6? It's basically, again, factoid is taking 3 plus 2. So basically it counts down the integers and adds them all together. So 3 plus 2, that's 5, plus 1, that's 6, plus 0, still 6. Basically down to 1. Divide by 1. That's how they get 6. Okay? It's a fun math thing. So you gotta enjoy that. Fun math. But mostly any, I believe, standard statistical calculator, those TIs, the Casios, if they should have an exclamation point button on theirs, which is the factoid button, should calculate these pretty easily. And again, we'll go and look at Excel or something like that as we move on. Next formula, the combination formula. Another counting formula useful to determine the total number of outcomes. which is a combination, is an arrangement where the order of the object selected is not important. Yeah, fun one. So, basically almost the same, except n factorial is divided by r factorial multiplied n minus r factorial. Just like saying factoid now. Basically our exclamation point. So, the Grand 16 movie theater used teams of 3 employees to work the concession stand each evening. There are 7 employees available to work. How many different teams can be selected? Okay. So, we have our 7, which is our n. So, again, we would count down 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. We'll get our top number. And then we'll have r factorial times n minus r factorial, which is 7 minus 3. So we have 3 factorial times 4 factorial. So basically, add 3 plus 2 plus 1. That will be 6 times 4 plus 3, 7 plus 2 plus 1. That's 10. Yeah. So we have 6 times 10, that's 60, then 7 plus 6 plus 5, so forth and so on. Either way, we come out to 35. Basically, because I'm trying to do it all in my head, I went out the calculator. Now, so, really the order doesn't matter. And logically, the number of combinations is always less than the number of permutations. In this example, 7 employees taking 3 at a time would create the possibility of 35 different teams. That's it. Alright, so now we've hit the fun part, practice problems. Yay, practice problems! Alright, let's see what we got. So, first question that we have. A survey of 34 students at the Wall College of Business. Yes, the Wall College. Showed the following majors. Accounting with 10, finance with 5, economics with 3, and management with 6, and marketing with 10. From the 34 students, suppose you randomly select a student. What is the probability he or she is a management major? What concept of probability did you use to make this estimate? Now remember, with all these practice problems, try and do them yourself before I explain how to do them. Try and pause. Hopefully, again, like that one chapter that threw in a question that wasn't even anything we talked about, it's not there. Okay, so which way were we going to use? Are we going to use the classical approach? We have to go back to the classical. Oh, wrong way. Classical approach. Or the empirical. Now, this is actually answering the second question, but we have to look at both of these, and we're looking at either the number of times the event occurs divided by the total number of observations, or the number of favorable outcomes. Now, we're really looking at the number of times an event happens and divided by the number total of observations. This one we're not. That's possible outcomes. We already know our total number of outcomes. Total number of observations was 34. So we're actually using the empirical probability for this practice problem. So back to the practice problem. You just hear click, click, click. So let's bring out our calculator. Hey, calculator is back in order. Then we lose the calculator. All right. So when we calculate this, calculator decides that it wants to keep going. There we go. So when we calculate and try and figure this out, since we're looking at management, so the probability of picking 6 managers out of the 34 of possible outcomes is going to be a long decimal. Again, do whatever Connect says on rounding. We're just going to round to 3 decimal places. So about 0.176. So about 17.6% chance that you're going to find a management major. Probability that he or she is one. Okay. So next one. Question 5. So in each of the following cases, indicate whether we're going to use the classical, empirical, or subjective probability that's going to be used. So we kind of already went back to classical, empirical of how they are done. So let's go through each one of those. A baseball player gets a hit in 30 out of his 100 times at bat. Probability is 0.3 that he gets the hit in his next at bat. Well, this one, again, it's using stats, using a number of events, divided by the number of outcomes. So this one's empirical. Again, not looking at the possibility. A 7-member committee of students is formed to study environmental issues. What is the likelihood that any one of these 7 is randomly chosen as the spokesperson? All right. So here we do have a set amount of outcome. We have 7, but it's the possibility of which one. We don't really have events that are actually forming, so this will be more classical. You purchase a ticket for the Lotto Canada lottery. Woo! Over 5 million tickets were sold. What's the likelihood you will win the 1 million jackpot? Again, this is another classical approach where we're looking at the possibility than actually having a defined number of outcomes. So again, we've got a classical item there. The probability of an earthquake in Northern California in the next 10 years above 5.0 on the Richter scale is 0.8%. Now, this one, again, is being based on seismological data, which ends up making it more empirical than subjectivity, because it's actually using historical data, which we can actually take and make a more of an educational probability. All right. Next question. A study of 200 advertising firms revealed that their income after taxes, under 1 million, 102, 1 million to 20 million, 61, 20 million or more to 37. Okay. What is the probability an advertising firm selects a random has under 1 million income after taxes? What is the probability an advertising firm selected at random has either an income between 1 million and 20 million or an income of 20 million or more? What rule of probability was applied? Okay. So, we have two ways of doing this. One, we can figure out, number one, we need to figure that one out first. So, we need to take our calculator. And let's figure out the possibility of under 1 million. Answer the first one. Well, that's 102 divided by our total, which is 51%. Now, we can take two different rules of approach. Oh, let me get that back up. So remember, there was two rules of addition, because either way it's the addition rules. We have the general rule of addition, and then we have the basic rules of addition. Either one you can probably use. So there's a complement rule. We have the general rule, which general does not apply because, again, we don't have similarities. So we're even looking at the complement rule and the rules of addition. Okay, either one will work. We can figure out the next two and add them together, or since we already have the one that's not part of the other two, we can use the complement rule. All right, back to our question. So, calculator. Since I'm looking for these two, let's go ahead and take 1 minus 0.51 will be 49% of those. Now again, I can do it the other way. Or I can take in parentheses 61 divided by 200 plus 37 divided by 200. And that will equal, again, to 49%. Either way would work because we found the odd one out. If we didn't have the odd one out, then we would just add the other one and still come out to the same total. So far, so good. These practice problems seem a little bit easy. We always say that before it gets a little bit tougher, huh? Alright. Next, the aquarium at Sea Critters Depot contains 140 fish. 80 of these fish are green swordtails, 44 female and 36 male. And 60 are orange swordtails, 36 female and 24 males. Wow. A fish is randomly captured from the aquarium. What is the probability the selected fish is a green swordtail? What is the probability that the selected fish is male? What is the probability the selected fish is a male green swordtail? What is the probability that the selected fish is either a male or a green swordtail? Alright. So let's pop out our calculator. Again, we're going to have a lot of different ones. Let's start off with the easy ones. Probability of the selected fish is a green swordtail. Now we do have 140 fish. We know 80 of these fishes are green swordtails. So if we take 80 divided by 140, probability is a little bit long. Let's see if we can extend. So yeah, and see a little bit better. But it's basically 0.5714. Again, a little bit if I want to go about 57%. Again, always check to see how many decimal places they would like to go. Okay, what is the probability of the selected fish is male? Okay, so first off, we got to figure out how many male fish are there. We have 36 plus 24. We have 60 fish that could be male. Divide that by 140. Will give us about a chance of picking a male fish around 43% of those fish could be male. Right? So, there's our first two. Easy peasy, lemon squeezy. Next, we're looking for the select fish is male green swordtail. Well, looking at the information for green swordtail, only 36 of those can be male. So that also gives us a good info. 36 divided by 140 says that about 26% of I have a chance of 26%, probability of 26, that I can pull a green male. Okay. We're not done yet. Alright, so next, they want to select the fish that's either a male or a green sword's tail. Well, judging by our numbers, we can do basically the addition general rule, because we can have this similarity that they could be male and green. So using that rule, we have to take our options, A and B. So we know one was the green swordfish. We know that they could be male. Total male was 60. So we're going to add 60 divided by 140. Basically, we're adding A and B. And then we're going to subtract the male, basically the similarity one, the male and green swordfish. So minus 36 divided by 140, because again, that's A and B. That's A and B together. Which turns out that the probability of selecting a fish that's either a male or a green swordfish. So basically, can be the green female is basically sitting at 0.74%. Okay, so again, we take the single variables A and B, which was the green swordfish and the male swordfish, swordtail. I don't want to say swordfish, but swordtail. And then we have to subtract it by the common, the ones that have them both of the characteristics, both of the variables. Okay? Yay! Waiting for one of those factoids to come up. Alright. 25. A local bank reports that 80% of its customers maintain a checking account. 60% have a savings account. And 50% have both. Okay? Again, we're dealing with that commonality where we have two separate ones, and then some that have both. That Disney and Busch Gardens example that we got. So if we choose a customer at random, what is the probability the customer has either a checking or a savings account? Number 2 asks, what is the probability the customer does not have either a checking or savings account? So first off, let's see if either or. So using our calculator, whoop. Calculator. There we go. We can go basically taking the 0.8 plus the 0.6, which is about 1.4, minus 0.5 will come out to 0.9, probably about 90%. Okay, so that's somebody either with a checking or a savings account. Now, if we want to find the probability of them not having either one, we take 1, basically 100%, minus our 0.9, will leave us to 0.1, 10%. 10% has neither. All right, almost there. Only have a few more to go. Yeah, just 2 more. So, question 29. Each salesperson at Pewitt, Sheets, and Hogan Insurance Agency, so PSH, is rated either below average, average, or above average with respect to sales ability. So this looks like more like a contingency table. Each salesperson also is rated with respect to his or her potential for advancement, either fair, good, or excellent. These traits for the 500 salespeople were cross-classified into the following table. And I gave away number 1 already. What is this table called? Of course, it's a contingency table. Yes. So if you didn't pause before I said that, then oh well on that one. What is the probability a salesperson selected at random will have above average sales ability and excellent potential for advancement? Okay, so this is going to use our multiplication. So, and the last one is construct a tree diagram showing all the probabilities, conditional probabilities, and the joint probabilities. We're not going to do that for our video. Sorry about that, but we're just going to look at number 2. So what is the probability? Well, taking our calculator. So we're going to look at the average sales ability, and we'll have an excellent potential for advancement. So first off, we need to total them up. So 45 plus 60 plus 45. Oh, well, I have above average. I'm thinking average all of a sudden. So 93 plus 72 plus 135 equals to 300. So we're going to have to take that total, 300, divided by 500. And this is going to get multiplied by the actual excellent. So 135 divided by 300. Watch out for those denominators. Reason why we're only using 135 divided by 300 is because there's only 300 in the size of above average that hit excellent. If we're going to the total of excellent, the 22 plus the 45 plus 135, then we use 500. So check out which totals you are using. So make sure you hit enter. Do not follow that. You always hit enter so that formula disappears. So we're looking at 27%. Okay. Now again, if we did the T chart, we would actually go to each one. We'll start with our sales ability, then go below average, average, above average, then fair, good, excellent for each one. And then we'll find the probability for each item using those totals. Again, if you want to use a tree diagram, you're more than welcome to. Those might actually help you out more in figuring out these multiplications. Okay. All right. Last question. So, an overnight express company must include 5 cities on its route. How many different routes are possible, assuming that it does not matter in which order the cities are included in the routing? Alright, so we want to know how many routes. And they must have an overnight, so they only have one overnight. Express company includes 5 cities on its route. Doesn't matter which way they go. Alright, so this is basically a 5 factoid. This is one of our factoids, but it's not big enough for an Excel factoid. So here on your scientific, you can do a factoid that way too. I love this little small little calculator. Makes life easy, but you see the N with exclamation. Make sure you hit how many, and then hit your exclamation point. And we have 120. That's it. There's 120 combinations that we could have with the 5 cities, because it doesn't matter which order that we're going into. And since we only have one route, basically it's one all the way around. It's not going to change anything. So it's 120. We're not looking at the probability of whichever. Just simple that. So they gave a really simple question at the end. Okay? But look forward to the homework video as we describe as we go with all of question 5. And there's probability. Will we dive deeper into it? We'll find out in later chapters. But basically, that's it. Okay? So thank you again for taking a bunch of statistics with your professor. Yes, with Professor Nerion. And I will see y'all next time.